So, let me, in preparation for, as a warning about the level of sloppiness with which I plan to present my analysis of one-parameter families of Morse functions, let me discuss again the Morse lemma and some of the subtleties involved. Sort of the sloppy way you might try to prove it, and then why you have to be more careful with that, right? So in the Morse lemma, if you're saying, suppose I just wanted to say, well, okay, df is transverse to the zero section, right? Can that tell me what? Can that give me local coordinates for the behavior of f, right? Well, let's just do the very simplest case where f is just a function of one variable, right? Okay. Then df is just f prime. Well, okay, df as a function from r to the cotangent bundle right, is really just df of x. I think the cotangent bundle of r is just r plus r, and that's just df of x equals x comma f prime of x. Right? And so, saying it's transverse is really, here's x, here's f prime of x. Saying f is transverse to the zero section just means that the graph of the derivative hits, crosses transversely, okay, somewhere. And so you might think, great, well, it crosses transversely. A function that cuts across it transversely is, basically just locally looks like a linear function. Let's you can reparameterize it, right? No problem reparameterize it so it cuts through the origin, let's say, make it nice and simple. And now you want, if this is just a function, from x to y, if I have, this is locally diffeomorphism, and I can just say, well, up to changing by coordinates in domain and range, I can make this look linear. This is equivalent to just a line. I can change coordinates in domain and range to straighten this little wiggly line out. The only thing is, if this graph was not transverse, then I couldn't do it. Okay, so I can straighten it out. What I'm really doing is saying it's equivalent up to change coordinates to its linearization. Okay, and the problem, of course, by using that to say that, well, f is really so then I can say, if this argument were right, I can say, well, f looks like f prime looks like f prime of x equals x, right? Or minus x, right? Plus or minus x depending on the slope. So plus or minus x, and then you integrate to get what f is. So f of x is equal to plus or minus x squared. That's a constant which you can shift out by. What's the problem with that argument? The problem with that argument is this straightening out involves reparameterizing in domain and range. But domain and range are linked, because if you change your x coordinates, you change your y coordinates as well, because the y coordinate comes from x, because it's the derivative of respect to x. Okay? So in the full general situation, this is a manifold, this is the cotangent direction, right? You change your coordinates, everything is the coordinates in the cotangent direction are intimately linked with the coordinates in this direction, right? And to go from, I could say, well, I could just willy-nilly change coordinates in either one, and so I could say as a section of an abstract bundle, I can find new coordinates on that bundle, so that the function looks so that df looks linear. But then if I want to go back and integrate to get f as just a function of x and say that it's quadratic because df was linear, I need to know that I was actually using actual coordinates that came from the pairing. And that's why the proof of the Morse lemma is more subtle than something as trivial as this. Okay? Now, I'm going to try to make arguments that are along this line, rather than more subtle arguments. Okay, but the point of the Morse lemma argument more or less shows that with enough care, things do work out this way, right? And so, when I started introducing parameters and so on, you want to, in principle, when these exhibit the same kind of care, I'm going to just argue that I can just change coordinates to domain and range so df looks like something nice, and then integrate that to get df, tell me what f looks like. And you have to realize that you really should have done it, you really should have carefully, what we really did in the move from the Morse line was you sort of carefully chose a changing linear reparameterization of the domain, so that gave us a changing linear reparameterization of the range, and that's your back. So if you go back and I claim that if you go back and look at that, and then one should, in principle, be able to iron out the way in which you fix this argument to make it correct should work in what I'm going to do today as well. Okay, so that's my caveat, and then I'm going to make arguments along this line. Okay. What I'm leading up to is trying to say that in a one parameter family connected to Morse functions, generically you only expect births and deaths of the x cubed plus tx. So I need to sort of say what kind of the genericity I want to get is a kind of transversality. Oh, remember the other sense in which one needs to be careful is saying that, well, I can wiggle things a little bit. If it's not transverse, I can wiggle it a little bit to make it transverse. I tried to be fairly careful about that, although the patching together in charts I was not very careful about. But even in one chart, you have to be careful because of the fact that, again, the fact that these things are linked, the domain and range have the coordinates are linked. So if you, I'm sorry, no, that's not the point there. The point is that if you wiggle, actually, that issue doesn't show up in one dimension, but in higher dimensions, if you wiggle the differential, you may no longer get something closed, right? And then you may no longer be able to integrate it back to get a function. And so we had to be careful that when we were perturbing our function, we were always perturbing it by adding differentials of functions, right? And now I'm going to make the argument, just wiggle things, right? I'm going to just say, well, wiggle the differential and cool. But again, that's the other lie that we did today. And again, we've carefully done that works. Oh yeah, one other cleaning up thing I want to say. In the in my super sketchy epsilon delta argument, saying that you can patch things together on charts, and you always have to make sure you don't screw up what you already did, right? How one thing you might worry about is if you want to, we have sort of this each chart we break it up into a central region where we use this nice linear perturbation that definitely makes us transverse, and then we taper that off with bump function. And we want that tapering off to be shallow enough that we don't screw up other things. And we need to bound that, and we need to think about how, what's the maximum number of charts that overlap, so that a given chart where you've already cleaned things up may have 27 other charts coming in and interacting with it, so all those other 27 other charts better not make things worse than 1/27th of your worst case. And so then you might think, well, that's bad because if I want, that sort of constrains, if the slope, I've got this bump function, well, linear, this is the derivative of things, right? It's linear, so that it's constantly taking derivative. And so in order for this derivative to be very gentle, I might, given a particular size ball, I might need to, use up a huge, very large angular region around the central ball where things are good in order to get a very gentle slope here, right? And then you might think, well, that's bad because if I have to use up a very large angular region, then I might then be forced to have more charts overlapping because I've constrained the size of this region on which things are good, and you might think you get into a spiral where the bad guy wins, right? Whoever's trying to defeat your epsilon delta argument. And so the one thing to say about that can help is if you're, again, this is maybe an argument that might be special to a compact manifold, is that if you think of it as a step-by-step process, you do one chart, then you in the good part of that chart, I've managed to bound bound things, the function away from non-transversality by some fixed amount, right? You probably have to pick a metric all the way at the beginning so you can measure all these things in some consistent way. You bound the non-transversality away by some amount. Now you move to the next chart, and you also are allowed to, we know that you can get things to be non-transverse by arbitrarily small perturbations. So for the next chart, you can actually, instead of trying to make this region large, so you get a very gentle slope, you can just make the actual perturbation small, and then you get a large slope. I mean, you get a steep, a gentle slope. Then you say, well, I made this perturbation small, so in this region, I'm less bounded away from non-transversality. So I might, but you can, as long as you have a finite number of charts to work with, right? Then each time you're getting less and less bounded away from non-transversality in each chart. But I think that the good guy can win that situation. It's sort of one extra tool. That's all we say about that. Okay, so generosity for F-C. So these are one parameter family of functions. So the generosity for a single function was really transversality with zero section. Okay, I set up the generosity last time, but I actually needed to add something to what I said. So the first thing is we want to think of, I want to think of df, for each t, df sub t is a map from the manifold M, so this is a map from M to R, and this is a map from M to the cotangent bundle of M, and now I want to do df t tilde, which is going to be a map from, it's just going to be a map from, it's going to be mapped from, let's say t is in the interval, I'll just say t is in R. It's going to be mapped from R cross M to R cross t star M. And it's just the thing that says t p to t t p. And I also have a zero section for that, and then I think I'm going to have a z tilde from R cross M. The point is I'm just thinking of this R cross T star M as now being a bundle over R cross M. Okay, so this is a section of that bundle. And then that zero section there is just TP goes to T zero at P. And so the first thing I want, I want two conditions. So the first condition one is that this df tilde is transverse to this new zero section. So in time it's transverse. But I need another condition now. Once I know this, then I know that the intersection of these two graphs is then going to be a one-dimensional submanifold of R cross M. Okay, and so the next thing I want is that if I consider the time coordinate, so t is a function from R cross M to R, and I want to restrict that to the intersection of these two things, so df t tilde intersecting with z tilde. So that's a sub, or maybe the better thing would be to say df t tilde inverse of R cross M, but I don't understand. That this is, if you count dimensions, this intersection is going to be, because it's transverse, it's going to be a one manifold. Originally, for each time to point, we already knew that. But then this is as time changes, you got these scribblings. I want that. So that's going to be a function from df t tilde intersect z tilde, this one manifold. In order to say it's a one manifold, I need this transversality first. Okay. Then I want that to be Morse. Which means it has a Morse function on a one manifold is not saying much, it's just saying the only critical points are parabolas, right? So I mean the picture is going to look something like this.
Is that a projection?
Let me try and draw the picture here, and then maybe that'll help. So I've got the t direction, I've got the m direction. This is that r. T is that r coordinate. And then I've got the t star direction. Or not, well, t star at each point. Okay? So this is the fiber direction. So this is a picture of r cross t star m. But it also contains in it r. So this plane here is symbolizing r cross m, and then the whole thing is r cross t star. And so z tilde this is just z tilde of r cross m. So I'm simultaneously drawing r cross m. I'm drawing that's the nice thing about vector bundles, is you can draw the base of the bundle in the bundle itself as the zero section, right? And then I'm drawing, and now df t tilde is going to be some surface, some kind of graph. This is the graph of a function from r cross m into the cotangent space, right? So this is some surface in here. That's df t tilde. That's the graph of that function. And then it's going to intersect r cross m in some one dimension. And so this is, that one manifold there is the transverse intersection of these two things. Does that help a little bit, seeing the picture? So far. And then the t function I'm talking about is the projection to that's the coordinate function t. So I'm just saying, so this picture, well, this picture, depending on how you draw it, maybe there's Morse. Maybe that might not be Morse, but well, generically it is, right? If I drew it randomly, it should be Morse, okay? Right, because what I'm really saying is this is exactly the set of critical points for each t, right? Because this is where the derivative is zero, right, in each fixed time. So in other words, if I take, just to clarify things, if I take df t tilde, intersected with z tilde, and then I intersect that with some fixed, t0 cross m, right, that equals the critical point set for f sub t0. I took a particular slice, t0 cross m is a particular slice there. And so I'm required, what I don't want is something like this, right? So I claim that the first thing I claim is which you should believe immediately is that if you didn't worry about preserving the closedness of df sub t for each t, you could just as a function, as a section of a bundle, you could perturb this section to achieve this transversality first. Okay, and then it's not hard to believe that you can achieve this Morse function, which is really another kind of transversality. But there you have to do you have to sort of, one way to say it is you can perturb. Actually, I'll talk about that afterwards. Let's just focus on this one first. Okay, so as a section, df t tilde can be perturbed to achieve 1, just using standard transversality arguments. But as I said, to do that and guarantee that it's still actually d of some function is more subtle, I'm not going to do that. I claim the arguments are essentially the same, and it's just worse. Without proof, I can do this. Keeping it as d of something. Okay, So that's the first thing I'm asking. First thing I'm asking you to swallow, and then the second thing I'll ask you to swallow, I claim it's actually maybe a little more swallowable here, is that now you may, so you got this transversality, so you've got this one manifold in there of critical points, but you may still have things like this happening. So there with a little more rigor, we can say we can actually perturb the function t, the time function, as a function. So we can get, so that's step one. Step two, we can perturb t to some function, let's say tau. It's going to be a new function from r cross m to r. It's very close to the original function t, such that tau restricted to this dft tilde intersecting z tilde is Morse. That's something that we've already looked at. I'm just thinking of it as a function. Any function can be perturbed by an arbitrary small perturbation to make it Morse. But other thing to remember about tau is that t as a function, I can think of t now in two ways. It's a function from r cross m to r, and it's a function from this one manifold to r. Maybe the one thing that is new here is that I want to perturb it as a function from r cross m to r, so that its restriction is Morse. And that's something a little bit more than we've done. It's not much harder. You just extend the perturbation. And the other thing is that the function t from r cross m to r had no critical points. Therefore, a small perturbation, since not having critical points is open condition, a small perturbation will still have no critical points when I restrict to r cross m. So tau from r cross m to r has no critical points. So, I mean, the picture is now, I can sort of sketch it here, the level sets of tau, precisely what would happen. For example, here we perturb it so that, maybe this is now what tau is going to be our new measure of time, right? And so these are level sets of tau. And now I just want to say, well, it may also be important to you that we started with it, let's say at time 0, we had a fixed Morse function. And if it was already Morse at time 0, then we already have all these conditions at time 0. And so if we do perturbations of things, we don't have to mess up what we've already done there. So maybe tau is nice. It's good there. So we can just, I'm just going to say that, so in other words, put it this way, so you basically can reparameterize. To be very fancy, I think of tau now as a function, I'm thinking of two ways, function from r cross m to r, and a function from this levels of this one manifold to r. As a function from r cross m to r has no critical points, therefore I can realize r cross m as a product. But it's not going to be sort of the same product structure. It's going to be a slightly perturbed product structure, so that tau now looks like the time function, right? So so that these are now the, I'm going to realize r cross m. The best way to say it is reparameterize r cross m, as r cross m again. I pick a diffeomorphism from r cross m to r cross m, such that tau becomes projection on the first coordinate onto r, and then once I've done that, these are constant time slices, and so now I've achieved the fact that so therefore so you get f of tau. It's not precisely the right way to say it, but we get a new. We take the original function f. Think of f as r cross m to r, right? And then I use tau as the time variable instead of t, and I'm done, right? So this achieves 2. So now I want to argue that if I have these two conditions, then either we're Morse at a particular time, or we've got this x cubed plus tx model for time. So that's that. Oh, the other thing that you might, I claim is basically in this argument, we at least sketch the proof that that any function can be perturbed by an arbitrarily small perturbation to satisfy these generosity conditions. And it also should be clear that those generosity conditions are stable. Transversality is stable, and then this property of t being a Morse function should be, if you perturb f sub t a little bit, you're going to perturb this one manifold a little bit, and then if you perturb an embedded one manifold inside a product manifold, you're not going to, the property of the projection of the first coordinate being Morse is also stable property. So this generosity condition generic, and generic in the sense that you can perturb anything a little bit and get it. It's generic and stable. Any given thing can be perturbed to have this condition, and if you have the condition already and you perturb it a little bit, you'll maintain that condition. And so now the claim is that this generosity condition uses local models. So first of all, if P is a critical point for f sub t, so that means that the point f sub t0, and I point t0, p is in df t tilde intersect z tilde, so t, z tilde, and the t function and t0p is a regular point, non-critical point for the function t restricted to that just means that I claim that implies that actually f sub t0 is Morse at p. So that's the first thing. Before we get to Berth's test, I claim that that's the situation where actually nothing interesting is happening. So that's the situation where we're somewhere, a particular t0, we're right there, and we don't have a maximum or minimum on this one manifold. Okay? And so the point there is that so notice I'm not actually saying something about what happens in the neighborhood. I'm not trying to do the one parameter Morse level at the moment. I'm just saying that at that fixed time it's Morse. And well, the argument there is just that if it's basically you've got this, I picture the surface df t tilde, the graph of it is transverse to the zero section, and it doesn't have a maximum or minimum. So if you just, what I want to argue is that if you just slice it right there at a fixed time, and then you still have the transversality you want, and all I have to argue is that this is because maybe the better thing to say is how could, I've got these two kinds of transversalities now. I've got dft tilde transversely intersecting z tilde, and I've got df sub t0 transversely intersecting z at that fixed time 0. And how could this transversality hold, but the transversality of fixed time fail. So the transversality of fixed time is when you slice it at fixed time 0 and look at just the graph in the end t star case, right? And the only way that for the full transversality to hold, but that transversality to fail, you need a what's maybe a useful sort of movie here. You can draw movies at each slice, and you can sort of draw different times, T1, T2, etc. And this is M and T star M. And so you might have something where you've got your graph of your function, your graph of df, your section, and then it intersects at two critical points. And then that would be transverse, and then the only way this transverse, if you then suddenly get to this parabola, that's precisely when your that's precisely from here with color codes. That would be two critical points coming together as one. But when two critical points aren't coming together as one, then in a particular slice you have transversality. Okay, so this is really because all of this implies these two things together imply df at t0 is transverse to z, zero section at t0. I didn't say that very well, but I think it's clear enough. The thing I want to talk about is what happens when you do have this failure of transversality. The only other case then is when you don't have a regular point, critical point, and claim in that situation you have this transversality but not that transversality. So case 2 is if T0 E is the point in DFT tilde, there's transverse intersection DFT tilde intersects E tilde, and T0P is a critical point for T restricted to well, this is a one manifold, so we know what critical points are. They're minima or maxima up to changing the time direction. Let's just assume it's a maximum, for example, right? And then we have a local picture which looks like R and T star M, and we have a maximum. Okay, so the other thing I'm going to do here is make an argument that pretends that M, that really does pretend that M is one-dimensional. Right, so there's my point, T0P. And I want to say, well, so what I'm really going to do is pick out one direction in M. And that's going to be my direction in which this birth depth is. I'm going to argue now that I've got an x cubed plus tx type model in one coordinate in M, right? So as usual, how do you pick out one coordinate and argue that in the other coordinates, things are staying standard? Well, this is a one manifold, right? It's one manifold moving around in R cross M, but I can locally project it back to M, and it's locally here it'll be a one manifold. You should be able to figure out that because I've got two critical points coming together, so locally it's when I project back into M, it will also be a one manifold in M nearby. And if I keep following these two critical points around, they can cross in M and so on. But near this point, I've just got two critical points coming together as one, and so that's a little arc in M, and I can use that arc, choose coordinates so that arc is X. And then I'm going to ignore the other coordinates for the rest. For the other argument, the points in the other coordinates, something standard should happen, which would be X squared. And so in that coordinate, Well, okay, now here's another, let's just, so in this coordinate, this picture now becomes actually realistic, a three-dimensional picture. This is the x coordinate in which this one manifold inside n is working. And so this is really just r cross r cross r. And how can I have a graph of a function from r cross r into r intersect the, this is xy plane. How can I have a graph of a function from xy plane to z intersect the xy plane transversely in a parabola? Well, it's got to be a parabola. The way you do this is you have a parabola. Vertical slices are also parabolas, but they rise up. So I claim that up to reparametrizing domain and range, and this is the hand-wavy part that I said before, where really you have to remember the coordinate here is linked to the coordinate there, and that's the fishy part. But I claim that change coordinates. So that this graph df sub t, well, let me momentarily just, so I've got a graph of a function g of xy, right? Just think of it very naively like that, but it's really g of x. This is really t, but I'm just momentarily thinking of it like that. And the graph of a function which intersects the xy plane in the parabola, it's got to locally look like x squared plus a constant, plus y. Okay, and I've got a parabola that's coming up and crossing the xy plane, and that's going to intersect the xy plane in the parabola, right? So I've got a trough that goes up and I slice it this way and I get a parabola. So I can change, now really this y is the t direction, so really what I'm saying is df sub t of x is equal to x squared plus t. That's the idea. And so then, the modulo, so that the hand wavy, the most hand wavy part is saying I can change coordinates, but remembering the fact that this coordinates here and here are linked, I have to be much more careful as to how I can change the coordinates. Once you believe you can change your coordinates to look like this, then you just integrate. I mean, this is really just saying f prime sub t of x, and so f sub t of x is equal to x squared dx. So the whole point is seeing things intersecting the xy plane as a parabola tells you that locally you've got a parabola moving up in time with the x. And that's it. That's the level of detail I plan on giving for this argument. Okay. Therefore, the local models are Morse for all but finitely many times, and then at those finitely many times, you have x cubed plus tx. Well, okay, so what about the other coordinates? That's the other thing. And so in the other coordinates, right, for the transversality, maybe this is worth thinking briefly about. For all this transversality to hold, in the other coordinates, it also has to be transverse, but I don't have this quadratic behavior happening in the other coordinates. So the other coordinates, say x, in another x coordinate locally, I should have just a linear transversality. So really, what about the other coordinates? Well, df is going to be linear in all of those coordinates except this one, right? And so the other coordinates I have df t of x is x squared, of x1 up to xn is going to be x squared, x1 squared plus tx1, and then plus the sum plus or minus the xi's. And then when you integrate back, you get the xi squared. Sorry, that's that. So what I want to do in the next, okay, so if you're deeply dissatisfied with the lack of rigor, then what you can take this as is a way to a sort of an algorithm for guessing what the local model should be, so that then you can go and try and be more rigorous and find what the local models really are. Okay. So let me give you an example of how you could do that for two-parameter families of Morse functions. And this is even more handy. So what about? So the question in a generic two-parameter family of functions, what sorts of critical points or what sort of critical behavior might arise? What about f sub s? So you can do the same thing. You can ask for exactly the same genericity conditions. And what do I mean by that? So the genericity conditions should be first that I can take d f sub st tilde. That's going to be a function. Now I need two time parameters, so r cross n to r cross t star n. I want that to be, I want that to intersect the appropriate zero section transversely. And now, when you count dimensions, this transverse intersection should be a two-manifold. Right? So that's the first condition is going to be this, and that'll be a two-manifold. Inside r cross n. And it's a two-manifold which, when you slice it at any fixed value of S0 and T0, should give you points. That's sort of the idea. And so what you now can think of, the next condition you want to think is that you want to consider the projection from, so let's let, pi from r cross n to r cross r, the projection on the first two coordinates, okay? Then you can consider pi restricted to this dfst tilde intersect z tilde, and that's going to be a map from a two-manifold to r cross r. Okay? Now, we haven't talked about generic maps from surfaces to surfaces, but I'm just going to appeal to your intuition a little bit. This should be generic. So what do generic maps from surfaces to surfaces look like? Well, they're either locally local diffeomorphisms. I mean, they have no critical points. So locally diffeomorphism. That means regular values. So that's, you should just think. So I've now got some funny surface in r cross n projecting down to R2, right? And either locally it's just a bunch of sheets stacked up, projecting straight down, or you can have, what are called folds, which look like exactly what you would think. So it's sort of pictures you have some surface like this, projecting down this plane, and so the image of the surface is just the left of the line. And there's one more thing that can happen, and by the way, the analysis of this can sort of, there's a huge bootstrapping process. I mean, understand, I'm just telling you some facts about generic maps to two dimensions, which actually can be derived from knowing about one-parameter families of Morse functions. But I'm not even going to go through that because it's a longer story. But everything sort of bootstraps dimension by dimension, parameter by parameter, and so the other picture that can happen is that you can have what's called a cusp, cusps, and the cusps look like, the best way to understand what a cusp looks like is the image of the singular set is going to be a cusp. And sitting above it, what you have is you have a surface that sort of folds back. Actually, the best way is I'm just going to, there's a surface out in space here projecting onto the blackboard. The image of the singular set is a cusp, so what does that mean? The surface looks like this. So as I slice across it, when I hit the cusp, it's repelled back. So this is, I don't know if you can see the surface at all, but I've just taken a sheet of cloth and I put a wrinkle in it, right? Which come two wrinkles that come together to a point. Okay? Those are the three things that can happen generically in a generic map to 2 dimensions. And the claim is that this condition, having these local models, is a stable condition. And so I claim that you can perturb the S and T coordinate functions so as to arrange that this transverse intersection has the property that when you restrict this projection onto R cross R, it actually ends up being one of these generic maps. And so now I want to think about what that would tell us about, remember, this whole surface we're talking about is the surface of critical points of this 2-parameter family of functions. And so what will that tell us about local models?
So is the picture where you have sort of a vertical cross-section look like a cube that's just not stable?
Correct, yeah. You have a cubic sort of cross R. Then you just pull it, right? Yeah. But if you have, but this you can pull this straight and just move this right. Locally, this can't need to go away. Right? These are stable things that locally you can't.
You're saying there's no other.
There's no other local models. So that's just something I'm throwing at you. I claim. When you think about it, really, what's going on here is you can again think of this as locally. Locally, you can call this time, and you can call this value of a Morse function. You got a 1-parameter family of Morse functions on one manifold, and this is a birth that can't compare. What is this? Locally, you call this direction time, and this is just a Morse function with a single critical point where nothing changes. Okay? So that's why I've said it's a bootstrapping process that bootstraps up from knowing about 1-parameter families of Morse functions to tell you about generic maps to 2 dimensions, and then keep going. So the bootstrapping process doesn't go on forever. It gets they're weird high dimensional phenomena. But so then you can say what would these now I want to sort of think about this right. So now I want to think about a picture in the S and the T plane and think about what these kinds of singularities can look like. And what I want to do is think that I've got a 1-parameter family of Morse functions changing by a 1-parameter family. Okay, so T is sort of the first parameter and S is the second parameter, right? And so at a fixed slice, we would see, when I want to draw, I guess I'm going to stop, I'm just drawing M now. And I'm no longer drawing, I can't draw, I don't have enough dimensions to draw the T star direction now. So I've got a picture of some surface inside M cross R cross R. And at each fixed S slice, I see some surface, right, and some curve. And so, for example, if this is at a fixed, if this is sitting inside a fixed slice at S equals S0, right, this curve, then I already know that in that time direction what's happening is this is a cancellation of a pair of critical points. These 2 critical points. Now what can happen is that as that proceeds, well, I may just have a fold that continues and nothing happens. I mean, so that would just be, I've got a 1-parameter family of Morse functions and maybe involving a depth of a pair of critical points, cancellation. And then as time goes on, maybe that cancellation moves around. So that's nothing interesting, right? What the interesting things happen, for example, is if this, I have a surface that now has I'm drawing the fold locus, so it's sort of, these are slices through the surface at fixed S0 values, right? And then I could have what I have is now is I have two cancellations of critical points coming together and canceling. Okay, the picture in terms of a surf graphic would look like I had a critical point born and then a critical point dying, and then that, you know, born and then they die again. Right? That's something you can see in a one-parameter family of Morse functions, and it's saying that in a one-parameter family of one-parameter families, such a thing can get smaller and smaller, and of course you didn't need it to be there at all, it disappears. So that's a death of a birth-death pair. Okay? Other things that can happen is you can, so that's if you have a maximum for this, you have the surface and you have a maximum in the S direction. You could have a minimum in the S direction, and the minimum in the S direction would be the opposite of this. You could also have a saddle in the S direction. So you could have something where it sort of does this and does this. And so that means that you have initially a fixed time, before this saddle time, this S0 value, you had T slices in which you just had two critical points moving along just happily. After this time, you have T coordinates, T slice, S slices in which, in the T direction, two critical points come together, cancel, and then are born again. So this is the situation where you have one parameter family, a movie of one parameter families in which you start with two critical points that could cancel but aren't canceling. And then eventually they come together and decide to cancel. And then, but then since you're doing everything locally, they cancel and then are born again. The most interesting one is what happens at this, at a cusp like this. So if this projection down here has a cusp, then what it means is that in the ST plane, you have some cusp. So you have a surface which notice this surface to the left of the cusp has one sheet, and in the middle of the cusp has three sheets. Okay, so something happens where you start with a surf graphic in which you just see, at a particular S0 value, you just see one. As you run across this S0 value, you look at a slice there, and this is time. You just see one critical point moving along with time. And then something happens, and then after that thing has happened, you have three critical points. You have a slice here goes one critical point, pair of critical points born, three critical points, some pair of critical points canceled, and then one critical point again. And that's precisely this swallowtail I mentioned before. So this is how you can see that. That's just, I probably won't ever do any more detail like this, but this is an example of how you can get these see how these higher dimensional singularities can arise in multiple parameter families of Morse functions.